So here we are doing some questions. First of all, from the work by energy. Okay, did you cover like how to calculate the work done
Yeah,
by different?
FS cos theta, and kind
Okay,
of he really wanted to make sure that we get the idea that work is a change in energy and can be treated as such for calculations and just for modeling like physical events.
all right.
Oh yeah, and
Um,
he even brought up that one situation, the one about the bullet and the block and the wood block that all the seniors were crying about on their tests when Aaron was with Ackland and
okay, like this one. This is a famous question, by the way. That like this rises up by certain
yeah,
height.
yeah, yeah.
Yeah, and then what is the basically what is the initial speed? Then determining like with the height, what is the final
Yeah,
speed and all
yeah.
that. Okay, we'll be doing that question. Okay, let me
Yep.
just, but like that will involve a little bit of the momentum also, the law of
Yeah, yeah,
conservation.
yeah. That's fine. That's fine. Momentum impulse, decently simple.
Okay, all right. So here I'm giving you a question right now. Okay, this will help me in understanding if you have understood the concept of work done properly or not. Right. So,
Yeah.
so here is the question. The question is again involving a little bit of the free body diagram actually. Okay, here you have the object tied like this. Okay, now so this is having some tension in the string here. This is the tension in the string. This is block
Okay.
A. This is block B. Okay, this is 10 kg and this one is 5 kg. Okay, consider G is equals to 10 meter per second square and mu, the coefficient of friction, as 0.1. Yeah, here this angle is 30 degree. Okay, so this will be going downward with some acceleration. Now till here you have already done these kind of questions, right?
Yeah.
Determining T and A is not difficult for you. Okay, what I want you to do is this B covers this particular distance. This is, let's say, 1.2 meter. Okay, it covers this 1.2 meter distance actually. Now when it covers this distance of 1.2 meter, so calculate work done. First thing, by gravity on B. Okay, second thing, by tension on B. Third, by tension on A. Fourth, by gravity on A. And also by friction on A. Okay, so these are things that you need to actually determine.
Oh,
Yeah.
these are
So
pretty cool, actually.
obviously you have to determine the tension first of all. Okay, so yeah, quickly do that.
I guess 50 sine 30 plus 0.1, 0.1, 50 cos.
30.
Yeah, 50 cos 30 is equal to 5 times, or minus ft, sorry, is equal to 5 times a. And we can strike out the 5s here because there's a lot of 5s. So what we get is what, 10 sine 30 plus 10 times 0.1 is 1. So 1, or just cos 30 minus ft is equal to a. Our second equation, of course, will have to be, oh, did you already do all the math? I don't
No, I'm doing the maths. Okay, you can go ahead.
Oh, okay. I was thinking just like create a simultaneous equation because A and whatnot, and you've already done the 4B. So then for B, it's going to be what? 10G minus FT. So just 10 times 10, 100 minus FT is equal to, wait, no. Yes?
Yeah, you're right.
Oh,
10A is equals to
no,
100
I screwed up. No, I screwed up for A because it should be FT minus this whole thing, right? FT minus that whole thing equals A, and then this is equal to 10A We can strike out a 10. No, we can't do that because, okay, and then we can't, okay, then that means that we can't do that for the other equations. So really, in summary, I am an idiot.
Your comments, man. Okay.
So 0.1 times 50 is 5, cos 30 is equal to A. Then what we also have is 100 minus ft is equal to 10A. Then we just add these together, 5A in the first equation. So we add these together. That should get rid of ft. 100 minus 50 sine 30. And these sine 30 and this thing actually have values which can be calculated by hand because they're special. A or right, yeah, these have to be minus 100 minus that is equal to 15A. Then what? Then what? Now that we've gotten here, we know what sine 30 is. Sine 30 is 1/2. So 100 minus 25 minus 5 into root 3 over 2. So 5 root 3 over 2 is equal to 15A. And all of this is divisible by 5. So 25, 3, and then just take out that. So then it's just 15 minus root 3 over 2 is equal to 3A. And then that can be solved as a decimal. So that gives us acceleration. But then
And here we got acceleration is 4.71. I'm giving the value, tension is 52.9 Newton. Okay, I'm giving you this value. Now, when I'm giving you this tension here, tell me what is the work done by tension on B?
What is the work done by tension on B?
Yep.
The work done by tension on B. It's going to be a negative amount of work. Because cos theta is -1 in this case because the difference in angle is 180 degrees. And then we know that 1.2 meters is like the distance it's doing that over. So it's just -52.9 times 1.2, which is a number.
So minus 63.5 joule. Cool?
Yep.
Yeah. All right. What is the tension on, what is the work done by tension on A?
The work done by tension on A will be positive because, S exists. Assuming that 10, I mean, just from a sensibility standpoint, or like a common sense standpoint, 10 kilograms moving 1.2 meters this way will result in a shift like this. So this should also move 1.2 meters. The displacement on A should be 1.2 meters.
So 63.5.
Yeah, it'll be basically the same. Yeah.
What is the work done by gravity on A?
Wait, which was 3? And then the work done by gravity on A. The work done by gravity on A, depending on, well, the vertical plane doesn't make, talking about the vertical plane doesn't make any sense because it does 0 work in this case, because cos 90 is 0. What that means is that we have force.
Yeah. By gravity on A?
Yeah, so then that's going to be 50 sine 30, which is 50 times 1/2 times 1.2, which is 25 times 1.2, which is
30.
Yeah.
So is that the right answer? 30?
30 joules, I guess.
Minus 30 joules.
Right, because the displacement is the other way. My bad.
Exactly. By friction on A?
By friction on A.
Friction is 4.33.
Oh. All right. If the friction is 4.33, then Negative 4.33 times, what was it? 1.2. Or 1, yeah, 1.2. So again, number 5.2 about.
Yes, 5.2 minus.
Yeah, minus 5.2.
Yes. All right. Absolutely. Now, see, the thing is, so over here, when you actually observe this whole stuff, okay, like specifically taking B only, okay, you can actually determine how much of the work is basically done, resultant work downward. See, by gravity, it is 1, and by tension, it is minus 63.5. That means there is some
Yes.
additional work, like overall resultant work is being done, okay,
Yeah.
downward, and that work done will be converted into the kinetic energy of this particular object.
Yes.
You're getting right?
Yep.
Yeah. All right. So the thing is, there are few questions that you are supposed to know. Change in the space. Okay. If there is change in the position, in the work done is basically always is the change in the energy. Okay. Actually, is just the change in energy of
Wait
one
one
type.
second, sorry.
So basically, the work done is change in specific type of energy, or different types of energy. In fact, like suppose, remember that like if suppose if here is a particle which is being lifted, this particular particle which is being lifted to this particular height. Okay, you're just lifting it up. You're just lifting it up. Okay, then in that case, just simple lifting it up. Okay, then in that case, so the work done is same as the change in potential energy. Okay, change in potential energy. Okay, this is let's say this is from the ground. This is ground level. Okay, and from the ground, this is at height h1. This is at height h2. Okay, so the work done is basically mg h2 minus h1. Okay, now this is one
mg
situation.
delta h.
Yeah. Now this is first situation. Here I'm giving you the second situation. Like here, what is happening that this object is shot upward. Okay, it has been shot upward. That means it is not losing the speed also. Like here, it is having v1. Okay, and when it is over here, it is having the speed v2 basically. Okay, so then this is h1, this is h2. Then in that case, the work done is equals to the change in kinetic energy plus change in potential energy. Remember, whenever we are doing the change, that means you are doing the final minus initial. That means half m v2 square minus v1 square, okay, plus mg h2 minus h1. Okay.
But wait a second, I'm a little bit confused. So the thing is that if we shoot a projectile up, what's essentially happening is it's losing kinetic energy to the gravitational field, but that energy is essentially.
If you are considering that, let's consider that also. But I'm talking about the rocket which is being launched upward with the increasing speed with certain resultant.
Oh, with an increasing speed. Okay. Yeah,
even if you consider with the decreasing speed, let me give you the example for that. So let me give you the example of what you are thinking. So let's say motion under gravity, and it
like
is
projectile motion basically.
Yeah, and it is just going upward. Okay, here it is having speed u. Here it is having v, and v is less than u. Obviously, that's what you mean, right?
Yeah.
And then it is h1 here h2. Okay, I'm not considering that it is reaching the zero yet. I can consider that also. Yeah, and here this is the ground level. This is the ground level. So over here, what will be happening is the work done will be equal to the change in kinetic energy. Now, work done by what? Work done by gravity, obviously. You're saying that it is losing the speed. That's because of the gravity. So it is the work done by gravity.
Yeah.
So work done by gravity in that case will be the change in kinetic energy, which is half m v square minus u square, okay, plus mg h2 minus h1 only. Okay, it is h2 minus h1 only. But the thing is, this particular thing, this work done by gravity will be zero in this particular case. Okay, overall. Why? Why this work done will be zero by gravity? Why?
The work done by gravity where again? Sorry.
Why the work done by gravity in this particular case will be zero?
When it reaches H2, or
yeah, when it is going from H1 to H2.
Because the two should be the same, no?
Because this change is same and
yeah.
opposite and opposite.
Yeah.
So they cancel each other. You're getting
Because
it?
u squared is greater than v squared, so they cancel out.
And overall change in energy is zero. Okay, there is no change in energy, right? The energy is being conserved. Yeah. You got it, right? Like over here, mgh1 plus half mu square, and over here this is mgh2 plus half mv square, and they are equal to each other. Okay, they both are equal. So when you say that these are equal, that means mgh2 plus half mv square, that is equals to mgh1 plus half mu square. When I take both the things on the same side, okay, then in that case, what we'll write, mgh2 minus h1 plus half mv square minus u square, and that's gonna be equal to zero. Okay,
that makes sense.
If it is under gravity, but if it is, I gave you the situation when it is being launched with the with certain upward resultant force. You getting it?
Yeah.
So so be it any condition, it is always this one only. Work done is always a change in energy. Okay. Now let me give you a situation that is the horizontal motion. When we are considering the horizontal motion, is there any change in the potential energy?
That can happen with springs, but not really, not that I know of. No.
We are considering the general normal translational motion, not with the spring. Okay, so here we are applying the force. Okay, and then it is going from U to V. Okay, this particular mass is going from U to V, but there is no change in the potential energy. Okay, so then in that case, the work done. Now over here, from here to here, the displacement is S, let's say. Okay, this is the displacement. Yeah. So then in that case, the work done is very simple. That is equals to force into displacement. Okay.
Yeah.
But that is equals to half mv square minus half mu square, right?
Yeah, change in kinetic energy.
Exactly. It's just the change in kinetic energy because there is no elevation in this particular case. Okay. Yeah.
Yeah.
You remember that in the very beginning, like we were discussing about a question which Acklin gave, that is the pendulum going up.
Yeah.
So then in that case, you should consider both the things, the kinetic energy as well as the potential energy, because it is changing the height also. It is changing the height. You're getting it, right? Okay.
Yeah.
All right. So so work done is this thing. So basically, what is F, by the way? MA into S, that is equals to half m v square minus u square. Correct?
Yes.
If I cancel m and then I write 2as, it is v square minus u square. There is a very famous equation, v square equals to u square
v equals u square plus 2as. Yep.
That is being satisfied with this also. Okay, you got it, right? All right.
Yeah.
Okay, here I'm giving you a question. Here is a checkpoint. An object is performing the circular motion. Okay, this is the circular motion. Vertical circle. This is the vertical circle. Vertical circular motion. Okay. The radius is 1.2 meter. Okay. Consider g as 10 meter per second square. Okay. And the mass of the block is let's say 0.5 kg. Okay. At this particular point, it is having a speed of let's say having a speed of, let's say, so this is of 20 meters per second, okay, at point A. So determine the speed at B, at C, and at D. That's the question. You got it right?
Yeah, so this is against gravity, basically.
Again, what?
This is against gravity.
Yeah, against gravity, vertical circular motion. Yeah, it is against gravity.
Hmm. I'm trying to think of approaches that have to do with like energy. Hmm. Can sort of be seen as just a simple circular function for this. But what I'm thinking is that at B, the total vertical displacement and the only axis that's the only energy loss that's going to be relevant is, or the only axis of energy loss that's going to be relevant for gravity is vertical. So the vertical displacement is 1.2 meters at B. And we know that its mass is 0.5 kilograms. What does that mean? We have a velocity, so I would assume a change in kinetic energy. Then we have an acceleration. Was it a v squared minus u squared equals, or 1/2 v squared v squared minus u squared. It just v squared minus u squared makes sense in that situation, but yeah. So there it's 1.2. That means it loses. What is the change in energy? We don't necessarily know. We only know an acceleration and a displacement. And if v squared is equal to u squared minus u squared plus 2as, and we have a u squared, and we're subtracting u squared from that, that means that in that bracket, we basically just have 2as, right?
Mm-hmm.
So 1/2 m times 2as should be equal to delta ke, I think. Does that make sense?
See, I'll show you something.
Hang on.
Okay.
Does that even make sense? Well, first it would probably be a good idea to just wait. What are we even calculating to begin with? The work done by gravity or the velocity at B, C, D?
We are calculating what is the velocity at B. Okay. What is the velocity at C? What is the velocity at D? Okay. These are the things that we are calculating.
Oh, okay.
Given that it is like this 20 meters per second at point A.
So the only way that energy is lost is by gravity in this situation, right? So it's best to think along vertical axis for velocity because, well, because the velocity will be only decreased by gravity. Which means that at 1.2, if we can say that 1/2 m times v squared minus u squared is equal to delta ke, then what that means is that because v squared is equal to u squared plus 2as, we can just say that it's u squared plus 2as minus u squared in those parentheses. U squared will go away, and then 1/2 m times 2as is equal to delta ke. We know a to be 10, we know s to be 1.2, and we know that this is 2. And then we know mass is 0.5, and times 0.5 is 0.25. So 0.25 times 2 times 10 times 1.2. So 0.25 times 20 times 1.2, which is 1/4 of 25 times 1.2, which is 6 meters per second, I think.
This is the thing. Half mvb square equals to half mva square minus mg into 1.2. That should give you the vb.
Oh, that's smarter,
So
actually.
easy. That's really easy. Yeah. And then the same way, for VC, I'll just do.
Does my method even like? Is my method even valid?
Your method was correct, but like, sometimes what happens is like you lose marks for going with the long methods also. Okay. That happens in ASB.
Yeah.
So that's why it's better to go with the appropriate method. Like if it is 2-mark question, why do you write like 4-mark stuff?
I don't know. The thing is, if we take 1/2 m times 2as, and like if it's correct, then that means that we can just take 10, 1.2, or in this case 2.4, and then we have like we can just do the same calculation with different numbers, and then we have something applicable to everything. But I guess in this case we kind of have the same situation happening. But then calculating VD, I mean, it would be just like the kind of, in using your model, it would just be the kinetic energy at C plus the GPE from falling.
VA square, what is that? That is 400 minus 2.4 into 10, so 24 basically. Yeah, so what is that equal to?
420 square root 424. That's
376.
Oh no, it's 400 minus 24, so 380 something.
376.
Yeah, 376. There it is.
And then taking the square root, what does that give you?
19.39.
19.39.
Okay, I guess I was wildly wrong.
Okay, same way you can actually get VC, that is equals to square root VB square, that is 376 minus 24 again, and that will be equal to 352 under root 352. So that is 18 point something.
Cool.
What is that?
Root 352 is 18.76.
18.76 meter per second. Okay. What do you think with without any further calculation? Can you tell me what is the speed at this particular point, VD? Without any calculation.
19.39 meters per second.
Absolutely. 19.39 minus meter per second. Right? Okay. All right. Yeah, now here. Okay. Yeah. Okay. Now over here, if I'm giving you, I'm saying that this is basically coming from a specific height from here. It was sliding downward on this frictionless thing. This is the frictionless surface on which it is sliding. So what is this height? What is this height?
Well, oh, wait. So this is modeling what? I'm confused.
You know, the roller coaster, like
like a loop-de-loop. There was actually an equation for that. There was actually an equation for this. The thing is that I think I went over something like this. Essentially, the GPE at the start has to be equal to the amount of energy.
Absolutely. Yes.
Or at least the height of the GPE.
See, there is no kinetic energy. It is
to start with, the thing is that if we know that at 20 meters per second it'll like make the loop, then what that means is that we have 1/2 m times 20 squared is equal to mgh.
Absolutely.
And then we can solve for h from there.
So that is the
What
h.
was the sorry. There's an equation for calculating whether or not, like, if you have a loop-de-loop, there's an equation for calculating whether or not something can actually make it through the loop. Hang on, I can probably derive this. If we have a certain radius r, just like the thing that we were using where
There is something,
the
we'll do that while doing the circular motion. Okay, we'll be learning about the looping loop thing and the vertical circular motion in quite detail. Okay, so we have that. Okay, there is this particular equation where we say that this mgh, okay, this mgh is equals to half m multiplied with 5gr, where r is the radius of the circle. Okay, so this m getting cancelled, this g getting cancelled. So h is equals to 5r by 2. This is the formula that we get. Okay, but here we are not doing that. This is different. Okay.
yeah, I know, but how do you derive that though?
Yeah, this 5gr is derived using the idea of the centripetal force. Okay, in the vertical circular motion.
Okay.
Yeah.
Okay.
So we are not doing that thing right now. Okay. So we'll do this thing later, not right now. All right. So now going ahead, here I'm giving you a question that an object is launched with certain speed. Okay. This is 20 meters per second in the horizontal direction. Okay. And it is hitting this particular level. Okay. What do you think will be the resultant speed? Okay. V over here when this is from 125-meter height. All right.
So it's a projectile motion question?
It's the projectile motion, definitely, but I don't want you to use any of the projectile motion.
Yeah, no Suvat. No Suvat crap.
Because after this, I'm giving you some different question after this.
Yeah. Let's think 20 meters per second. 20 meters per second horizontally?
Yeah, horizontally, yeah. It is. Yes.
Velocity will be 20 meters per second. I guess I can just use 20 meters per second as a velocity. The only issue is that the only place it gains, I don't know, it just makes more sense to. Does that make more sense? As 0 of that. So the only thing that like my brain is kind of like second guessing itself on is that we have 20 meters per second as a horizontal velocity vector, but the vertical velocity vector is independent. So does it make sense to calculate the vertical velocity thing as its own separate mgh equals half mv squared sort of thing?
Wait a second. Work done, energy, power, all of these are scalar quantities. They are not vector quantities.
Yeah.
Okay. Yeah. So whatever is the energy over here, same is the energy over here.
Okay.
Irrespective of the directions.
Yep. Sounds good. Yeah. All right. In that case, we have 20 meters per second as our yeah. Okay. Sure. 1/2 m20 squared plus mg 125 is equal to 1/2 mv squared. We can get rid of m. So half of 400, which is 200 plus 125 g. Are we assuming that g is 10?
Yeah, g is 10.
G is 10. Okay, so is equal to 1/2 v squared, which means that was that 1,450 over times 2 is equal to v squared. What? Or no, the square root of that is equal to v. Sorry, so then that's what, square root 2,900?
Yeah, tell me. Where is
equal to v.
53.8.
53.85, yeah. 53.85.
Yeah, so this is the speed. Now tell me, what speed is it? This one or this one? I mean, this at an angle or this particular one? Which one is it?
Which speed is the angle at?
I mean, this is one option, first option, and this is second option.
Oh, so this is just purely qualitative?
Sorry?
Is this purely qualitative, or do we have to calculate this?
No, qualitative.
Then it's going to be the first option, because there's still a vertical component in there. You can't just ignore it.
So 53.85 is the total speed. Yeah. So with that also, you can actually determine the vertical speed. Okay. So 53.85, that is equals to the vertical speed v square plus the horizontal speed gonna be the same, 20 square. So with that, you can actually determine the vertical speed also. Right? Clear?
Yep. Yeah, that makes sense.
All right. Now my question is gonna be slightly different from this. Okay. So see, the thing is, sometimes there has been like like 1 year, like when you got a question that it is coming from here, then it is going like this, and then it goes like this. Yeah. So this kind of route is there. Okay. You are given this kind of route. This is with respect to the ground. Like this. Okay. So if if this is a certain height, if this is the height, let's say this is 125 meters. Okay. Yeah. And you're defined all the heights. You're having all the heights defined basically. Okay. Here the speed is 0. Okay. So this is, let's say 75 meters. This is, let's say 90 meters. Okay. This is 0. Then this one is 45 or 60 meters, and this is 0. Okay. Yeah. So the thing is, consider that there is no friction. Okay. Then you will be asked to calculate the speed at all the points. Okay. That is point A, B, C, D, and E. Okay. At all these points, you need to determine the speed. You got it right?
Yeah, I mean, that seems like a decently lengthy process, but
okay. Now, wait a second. You also need to determine whether this will be touching B or not, and this will be touching C or not. Given that,
I think I got a similar question in like 8th grade or something. This is okay. I don't know. We'll see. We'll see. I don't know.
So I want you to work out on this thing in as your homework. This is, let's say, 20 meters. Okay, and from here to here, this is 100 meters. Okay, you're given this much information. What you have to determine whether it is gonna touch B and C if you're given M to be equal to 10 kg. Simple. Okay.
And we assume gravity. Do we have to work with gravity for this, or is it more of a?
You need to think of the normal reaction. You need to think of a lot of things, in fact. Okay.
Because the thing is that. Yeah, the thing is that essentially we're changing between kinetic energy and gravitational potential energy. The thing is, we start at a height higher than every single other point. What that means is that because energy is conserved, it's literally impossible for us to not have the energy to get to any point below 125 meters. So I think that's the case, right?
Yeah, see, the thing is, yes, absolutely. The thing is, it is going with certain speed. It is possible that like it may go in the air. Okay, it's possible. Now, what's the condition that it doesn't go in the air? You need to think of that condition. Okay. You know, like when you are driving, if the speed breaker comes, if you're not slowing down,
that its speed is not too high that it misses that it just kind of.
Yeah, if it is very high,
that's more complicated.
Yeah, if the speed is high, then you go in the air. Okay, if the speed is not very high, then you remain contacted to the air. You remain with the
contacted to the speed bump. Yeah, you say you remain on the ground. Yeah.
Yeah, that's why the speed breakers are there, right? So that's what I want. Like considering that, like this is at a distance of 20 meters. What do you think? Whether it will go in the air or not? Okay. You need to think of the normal reaction. You need to think of a lot of things, in fact. Okay. The thing is, you need to think of the normal reaction. You need to think of a lot of things, in fact. Okay. The thing is, you need to think of the normal reaction. You need to think of a lot of things, in fact. Okay. The thing is, you need to think of the normal reaction. You need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you need to think of a lot of things, in fact. Okay. The thing is, you Second thing that if it is going in the air, okay, if it is not going in the air, okay, then whether it is going horizontally, and if it is going horizontally, is it hitting C or not? Okay, that is also the question. Okay, to understand the question, you can refer the recording, the end part of the recording. We'll stop here.
Okay.
Okay, but like if you're having doubt, if you're having any doubt,
are you out of time, or because I was gonna ask about momentum and impulse.
Oh yeah, please ask here. Tell me.
I don't know. I just we haven't started it yet, but I guess we're going to. So momentum is MV, which makes it kilogram meters per second. Yeah, kilogram and meters per second. So it's basically force per time, right?
Force into time.
And then a change in that, of course, is going to be the impulse.
See, we define force. We define force as mv minus u over t, ma, right?
Yeah.
This is nothing but
MA.
mv minus mu over t. Okay.
So change in momentum.
This is change in momentum over time. So obviously, change in momentum over time is f into t. Now, when you plot a graph of f versus t, the graph area under the graph, this gives you delta p. Now, this is nothing but the impulse.
Impulse.
Yeah.
But then with the slope of that, because the thing is that if force is mass velocity rather, then wouldn't the slope of that give us momentum? Or
no.
When the slope of that gives momentum? Oh.
If you're having momentum versus time, then the slope gives you the force.
Okay.
But when you're having force versus time, the slope doesn't give you anything here.
Also, can we take a look at the bullet question, or do we not have time for that?
Sorry, which question?
The bullet question, the bullet and the pendulum block.
Oh yeah, sure. Let's do that question here. Now that is involving the conservation of linear momentum. Okay, so you should understand that the total
momentum is constant. It's always conserved. Yeah.
Okay, so I'm taking some random numbers. Okay, let's say that this one is 1.8 kg, and here we have a bullet. Okay, that is 200 grams. So basically 0.2 kg. Okay, yeah. Now the question is that when it hits the bullet, it gets embedded in it. Okay, and it goes to the maximum height before it basically it is the maximum height that it achieves. Okay, so the height which is achieved over here is, let's say this height is 1.2 meters. Okay, yeah. So the question is, what is the initial speed, okay, of the bullet? What is u? All right, and what is the speed when the bullet got embedded in it? Okay, you got it right.
Sort of.
Yeah. What is the speed? So the speed when the bullet got embedded in it. Okay. And what is the speed before it hits the block? So we are having bullet, we are having the block.
Okay, yeah.
Here with the red, basically I'm showing a condition in which like the bullet got embedded.
Yeah. So essentially the point where a bullet contacts the block, what is the velocity?
Absolutely. So how to do this kind of question is damn simple. Consider g is equal to 10 meters per second squared, first of all. Okay. So
so
now this is the speed over here is 0. Okay. So obviously the change in kinetic energy equals to the change in potential energy, right? So the total mass of the system gonna be 2 kg. This is 2 kg mass because 1.8 kg.
Because the bullet is embedded in it. Oh my god, that is wow, that's annoying. That's why all the seniors got it wrong. Oh my god.
So this is the change in potential energy, right? And that is basically the initial kinetic energy, half mv squared. Okay.
Yes, but the issue is that isn't there also a horizontal change in or displacement involved?
Remember, when you're dealing with the energy, no direction. Forget about the directions. Okay. whatever is
Yeah, but it's not even a matter of directions. It's just that the change of energy is work. There's a horizontal displacement as well as a vertical displacement, which means
absolutely.
that the overall displacement we're looking for is like this. It's more of this hypotenuse as opposed to just this.
Yeah, correct. So basically, ultimately, you just need to deal with this change in the height and then the initial and the final speed. That's it. Okay. So we get V over here. We can get V easily. Yeah. This is
Okay.
half into 2 into V square. What is that?
Yeah,
V?
yeah, yeah.
V is the speed when the bullet got embedded in it.
Yeah, when the bullet hit the block. Yeah.
All right. So what do we have? This is 12 to 24. V is equals to under root 24. So what is that equal to? 4 point
4.8989979. So basically 5 or 4.9.
No, 4.9. That's better. Okay, 4.9 meter per second. Okay. All right. So 4.9 meter per second is the speed. Now let's talk about the momentum. Total initial momentum gonna be equal to total final momentum. What is the initial momentum? Initial momentum Pi, that is equal to 0.2 times u. What is the final momentum? Pf, that is equal to 2 times 4.9. Agree?
Okay, so the initial momentum 0.2 u, final momentum 2 times 4.9. Yeah.
You can say,
okay.
just to be clear, 1.8 into 0 because it is at rest.
Okay.
And then why I'm taking 2? Because that's the combined mass.
Okay, yeah. That
all right.
sort of makes sense.
Yeah, so then in that case, 0.2 into u, that is equal to 2 into 4.9. So u is equals to 2 into 4.9, that's divided by 0.2, that is equals to 49 meter per second. That's it.
Cool.
Okay.
Yeah.
Easy, right? It's damn easy, actually.
Yeah, but you have to make the realization that like the bullet gets embedded, not that the bullet just kind of.
Exactly. You know, one thing there is, yeah, this particular question is like fine, but like there is a question that like to what depth, to what distance the bullet is getting embedded in the block, depending upon the elastic force also. So, but like those kind of complications are not there in IB yet. Okay, so feel
why not? Why not though?
Because that's a different concept. Like it is the concept about the materials basically.
Yeah, you have to know the material. Yeah.
All right, cool. So we'll stop here. Okay, you have a question. You have a question to do, and this is just the just to understand like the concept basically. This kind of question doesn't come in the IB.
Yeah. Okay, sounds good. Yeah.